Hello everyone and welcome to my channel. Today I would like to bring you another problem in classical mechanics. This course is meant for undergraduate students getting a degree in physics, bachelor degree in physics or engineering or math. And we continue reviewing some fundamental concepts in mechanics like acceleration. And today I would like to bring you something about velocity, more precisely addition of velocities. And we are going to do it with this exercise this is from a book, a very good book, from Sounds Outline series, Theoretical Mechanics by M.R.Spiegel. This is a wonderful book. It has loads and loads of problems, solved problems, and other supplementary problems proposed for the student to tackle. And I would like to bring you one of those supplementary problems from chapter one. At the end of chapter one, is problem 144 and 145 of this book, and it deals with a river. The river has the current of the river has velocity, and there is a rower in a boat also rowing with velocity, and we will have to add both related to the shore. So we will see how relate the velocities, the river velocity and the boat velocity, how to add them related to shore. It goes like this. A boat leaves point P here, on one side of a river bank and travels with constant velocity v in a direction toward point Q on the other side of the river, directly opposite to P and distance d from it. So he starts here. Here we've got point Q, distance d between both, and the rower is always rowing toward Q in radial direction toward Q. If r is the instantaneous distance from Q to the boat, this distance here, theta is the angle between r and PQ, and the river travels with a speed v horizontally, like this. The current travels like this. Prove that the path of the boat is given by r equal this formula here. This secant of theta divided by secant of theta plus tangent of theta powered capital V, the rower velocity, divided by the current velocity. Prove that if both velocities are equal in magnitude, the path is an arc of a parabola. You see here this formula is given in polar coordinates. This is all the situation happens in a plane, and this is given in polar coordinates. So let's get started. Okay, here we have the drawing, and we will use polar coordinates. We are asked to arrive to the formula that is given in polar coordinates. So we will work in polar coordinates. So we are used to work generally as when we start in Cartesian coordinates, x and y. And here we have unitary vectors in x direction, horizontal and vertical direction, y vertical. Okay, so if I put myself here where the rower after some time is, and I take unitary vectors radial in a direction where the radius from Q, radial distance from Q increases, this is u sub r, radial vector, and here perpendicular to u sub r is this u sub theta that is directed towards in angle increasing, both perpendicular. So we have to relate all of them. And if we see here from the drawing, this angle here, theta, of course, is the same as this angle here. This is the radial direction, this is the vertical, so this angle is theta. Okay? And if this is 90 degrees, because they are perpendicular, this is again theta. So we are going to relate both vectors. So we decompose the radial vector in Cartesian, and this is given by u sub r is sin of theta in the x direction, plus cosine of theta y direction. And if we decompose u sub theta, it will be cosine u sub x minus sine u sub y. And why do we do this? Because the position vector of the boat about q related to q in a certain time t in polar coordinates, here is the boat, it will just simply be the radial distance directed in the radial direction. And we are given velocities. All we know as data is the velocity of the river and the velocity of the boat. We know that at some point we will have to zoom it, so we'll have to calculate the velocity related to q. If we have the position vector, all we have to do to get the velocity is, as we know, derivate. We get the derivative in time. So the velocity of the boat related to point q, is the derivative of the position vector related to q in time. So it is just the derivative of the radial distance u sub r, which is the position vector, and we have to derivate in time applying the chain rule, Leibniz rule. So what do we get? The derivative of the coordinate r with time, u sub r, plus the radial distance and the derivative of the radial vector, because the radial vector depends on time as well, varies in time. As we see here, in the drawing here, it is not the same as the rower moves. You see here, he arrives to this point from P, and if he continues, the radial vector is always changing. And we see here, x and y vectors, unitary vectors, are constant, but u sub r and u sub theta are not. So if we derivate this expression here in time, we just theta depends on time because it's varying. We get cosine of theta u sub x minus sine of theta u sub y divided and multiplied by the derivative of theta with time. And what is this here? This vector here is u sub theta. As we see here, we decomposed it before. This is u sub theta. So the derivative of u sub r unitary with time is just the derivative of the coordinate theta in time multiplied by the unitary vector u sub theta. We could also, now we don't need it, but u sub theta also depends in time. But here we finish because we don't need the derivative in time of u sub theta. But just if you want to know, it also derivates it also depends on time. So here is the derivative in time. So finally, the velocity of the boat related to q is r dot u sub r plus r theta dot u sub theta in polar coordinates. But also the velocity of the boat related to q is by addition of velocities, because it is also, the boat is also affected by the current. So it is the velocity of the boat related to the river, which is this v, capital V here, plus the velocity of the river related to q. This is intuitive to understand. If we are in the river, we imagine ourselves we are in the river rowing, our total velocity is not just the velocity we are rowing with, is the velocity we are rowing with plus the velocity of the current of the river. And the velocity of the boat related to the river is minus v u sub r in the radial direction, but directed inwards, directed to q, towards q, plus the velocity of the current of the river, which is horizontal. This is small v, horizontal in the direction of increasing x. But this vector here, the velocity of the boat related to the river, is in polar, is related to polar vectors, and this is Cartesian vectors. This u sub x is Cartesian vectors. So what we have to do now is relate the u sub x in polar vectors. But this is easy. From this graph here, we can just decompose u sub x in the radial vector and the azimuthal. And we see from the drawing that u sub x is just sine of theta of theta u sub r, this length here, plus cosine of theta u sub theta. If we wanted to decompose u sub y in a similar manner, it would be cosine of theta u sub r minus sine of theta u sub theta. And this is what we get. We just substitute and we get minus capital V u sub r plus small v and u sub x. This is u sub x. We see it, we got it from the drawing. Sine of theta radial direction plus cosine of theta azimuthal direction. So we just group terms the radial term. So this is v sine of theta minus capital V radial direction plus v cosine of theta u sub theta. But as we saw in the previous slide, the velocity of the boat related to q, this is also in polar coordinates, r dot radial direction plus r theta dot u sub theta. So all we have to do is equate, make equal. R dot then must be equal to this. So R dot is V sine of theta, small v sine of theta minus capital V. And R theta dot is V cosine of theta. U sub theta here, the same than this. And all we have to do now is solve these differential equations. If we go for this one, the second, this is quite easy. We just substitute. You will see later why. I start with the second one. We will do a magic trick. So theta dot is V cosine of theta divided by R. Okay, and R dot is just simply the derivative of the radial coordinate with time. But we are looking for, the solution is we want to know the radial coordinate depending on theta, that formula in the first slide about the secant and the tangent. So if we apply the chain rule, the derivative of r with time is the derivative of r respect theta multiplied by the derivative of theta with time. And this is equal to v sine of theta minus capital V. But this derivative of theta with time, it is what we have from the second equation here, right? So we see that this is equal to the derivative of r with theta, then therefore is v sine of theta minus v divided by theta dot. We just substitute and we get v sine of theta minus capital V divided by v cosine of theta divided by r. So this is grouping and putting a bit more elegant. This is r multiplying the tangent of theta, sine divided by cosine is the tangent, minus v, capital V divided by v, this v with v, and the inverse of the cosine is just the secant of theta. And all we have to do now is integrate this differential equation. It's separable and it's first order differential equation. Now the limit of integration, so if we want to integrate, this r goes down here, dividing differential of r, and this goes multiplying, we integrate. So the limits of integration, the radial coordinate it starts at P, so the radial coordinate is D, and an arbitrary point in its journey will be R, simply R. And the angle starts when theta is 0, when the boat is at Q, the angle is 0, and a certain point here in its journey will be theta. If we integrate this first integral is immediate. This is just the natural logarithm. The integral of the tangent is the natural logarithm of the cosine. And then this term here will give this integral, the integral of the secant of the angle. And this integral here, if we don't know how to calculate it, we just go for a table. I went for a handbook, and I will list this handbook that I use in reference 1. And in the table, we go to the table and we see we use this integral here, that the secant of certain a constant multiplied by x Differential of x is this term here, 1 divided by n, the natural logarithm of the secant of ax plus the tangent of ax. So we have this integral here as well. So, okay, we just substitute in the formula, okay? And we just play a bit carefully. So the logarithm of the quotient of r, small r divided by d equals the logarithm of the secant, okay, plus the logarithm of the secant plus the tangent power minus v, capital V, divided by small v. All I use here, for those of you that may not be familiar with logarithms, the logarithm of the subtraction is just the logarithm of the quotient. Logarithm of a minus logarithm of b is the logarithm of a divided by b. This is what I use here. Okay? The logarithm of cosine, the inverse of the cosine is just the logarithm of the secant. I use this property here that a constant b multiplied by the logarithm of certain a is logarithm of a power b. And this is what I did also as well here. I powered capital V divided by V in secant plus tangent. Okay. So if we arrange this carefully, this is the sum of the logarithms, is the logarithm of the product, and we get this formula here, that r of theta is the d multiplied by the secant of theta divided by secant of theta plus the tangent of theta power capital V divided by small v. Just arrange carefully using the properties of logarithms. This is the formula we were asked for. And now we will play a bit to see if this makes sense and what does it mean. What happens when the angle is 0? When the angle is 0, the particle, the boat should be at P. The boat should be here at P. If we substitute theta equal to 0, the secant of theta divided by the secant of 0 plus tangent of 0, this is just d, because this is 1, this is 1, this is 0, 1 power v divided by small v, this is just 1, secant of 0 is 1, so we have d. Now we take this formula and we arrange it a bit carefully. The secant is the inverse of the cosine, and here we take the cosine from the secant also, we take it out. Here the cosine is dividing, this is 1 divided by the cosine, and this is sine divided by cosine, we take it out, okay, and we multiply here, we solve this fraction here, this goes up, multiplying with b, and we get this, d cosine of theta power capital V divided by small v minus 1 divided by 1 plus sine of theta capital V divided by small v. And why do I do this? Because to understand what happens when the angle is P over 2, that is when the boat will actually arrive to the shore, we want to know what is the radial distance, okay? So we just substitute in the formula. When the angle is pi over 2, the boat will arrive to the shore. And here we have to distinguish two cases. What happens when the velocity of the rower in magnitude is larger than the velocity of the current of the river? If capital V is greater than small v, this is greater than 1, so it will be positive. This power here, this exponent here is positive, and we get that the radial coordinate is just 0. Okay, sine of pi over 2, this is 1, but this will be 0. Cosine of pi over 2, this is 0. Powered by something positive, this is 0. The cosine of pi over 2 is 0. So what does it mean? That the boat will actually reach Q. The final radial coordinate of the boat will be 0 because it will be at Q. the boat reaches Q. And this is intuitive because if he is strong enough to overcome the current, he will actually reach the point he wants to arrive to. And what happens if the rower, the velocity of the rower in magnitude is less than the speed of the current? Then this exponent here is negative, so we are dividing actually by 0, d divided by the cosine of pi over 2, and this is d divided by 0, and this is infinite. So what actually happens is that the current will drag the boat, and the radial distance from Q will be infinite because the boat will be dragged by the current without actually never reaching the shore. And what happens if both velocities are the same magnitude, have the same magnitude? Well, then this exponent here is just 1. So this is d secant of theta divided by secant of theta plus tangent of theta. This is just d divided by 1 plus sine of theta. I take this here and multiply it by r, and I have r plus r sine of theta. This is equal to d. And if we look at the drawing, okay, this is axis y and x. Okay, and what is the radial distance? The radial distance is just the square root, right? X squared plus I squared, and r sine of theta, this is just x. So this is the same as this in Cartesian coordinates. We manipulate it a bit, we take the square, we take x here subtracting, and we have that x squared plus y squared is d minus x squared, and we develop the square here, the square in the brackets, and what we get finally is that this x squared cancels with this x squared, and we get finally, solving for x, that this is equal to minus y squared divided by 2d plus d over 2. And this formula here is a parabola centered at point x equals 0, y equal d. And as we see here, what happens when y is 0? When y is 0 is when the boat will reach the shore. So it will reach the shore actually at a radial distance d over 2 from Q. Okay, the references I used for solving this exercise is, of course, M.R.Spiegel, Theoretical Mechanics, reference number 2. This is at the end of the chapter 1. This is problem 1, proposed problem 144 and 145. Also from M.R.Spiegel, I looked at that integral of secant of theta. M.R.Spiegel and Seymour Lipschutz, and John Liu, Mathematical Handbook of Formulas and Tables from Sound Line series, McGraw-Hill. This Sound Online series also from McGraw-Hill Company, this Theoretical Mechanics, very good book with lots and lots of solved problems. And if you want to overview these concepts of adding velocities and acceleration and these fundamental concepts, the ones I proposed also in the previous video, Ebel, Classical Mechanics from Imperial College, Landau Lifshitz, and Marion would do. They give very good introduction to this concept. Okay, thank you all if you've made it this far for watching the video. I would like to thank you all, and let me finish the video with the last verses of a very beautiful poem written by the English poet Carolina and Bowles called The River. Thank you all, practice math, and stay curious. Bye-bye.